I'm a clinician scientist, I'm a glaucoma specialist, and I deal with glaucoma, which is a disease that is most commonly associated with high pressure in the eye.
That interocular pressure can cause damage to the optic nerve, often resulting in vision loss or blindness. About 3 million Americans have glaucoma, although about half don't know it yet.
The one way we have to treat this disease is to lower the pressure, but actually it doesn't work in a significant portion of our patients. And in fact, there's a lot of patients who have disease despite having normal pressures.
Dr. Saeedi, an ophthalmologist at the University of Maryland School of Medicine at the University of Maryland, Baltimore, works hand in hand with research partner and collaborator, Dr. Giuliano Scarcelli, a bioengineer from the A. James Clark School of Engineering at the University of Maryland, College Park.
Every material, because it's not frozen, has natural fluctuations. Those natural fluctuations are basically little sound waves, right? So we are just creating an instrument that is sensitive enough to see those, right? To measure those, to be sensitive to the change of tissue due to these microacoustic waves that are around the tissue.
The instrument that Scarcelli and his team have created uses laser light to interact with the eye's tissue. Its operating principle is called Brion light scattering, a measure of how the natural sound waves within the eye mass scatter the light, altering some of the wave's frequency and energy, yielding telltale signs about the stiffness of the eye's tissue.
And it works for the cornea, which is the tissue for which we are measuring mechanical properties. So when I moved here, I immediately met Osamah, and we started talking, and eventually we got to the point that the technology could be useful for some of the problems that he's working on, specifically glaucoma.
So, to sort of, not to get too detailed about it, but it's not just about the pressure, it's about how the eye handles the pressure. We want to understand the biomechanical properties of the eye. So you could push against some cotton candy and you'll push all the way through. If you put the same force against this table, nothing will happen, right? So what is causing, what is the mechanical properties of the eyeball itself? And in this case of the cornea, the front part of the eye, that will tell us something about people's risk for the disease.
Knowing the risk factor, Saeedi says, allows doctors to more effectively treat and prevent the disease.
So we have this blinding disease. We know that there's some mechanical aspect to it, but we don't understand everything about that. And so what our bioengineers help us do is they help us understand better the very really new biomarkers and the very specific aspects of the biological tissue that make people more likely to get this disease.
But the sense of urgency, collaborative energy, and shared commitment required to overcome challenges, test theories, and explore new ideas is not easily sparked by Zoom meetings.
The proximity is what enables to build projects from the ground up together. Zoom doesn't work for this.
I think what you'll see with 4MLK is that people will be, eager to collaborate with each other, and it will be a natural thing, right, for people to just be in close proximity, to get a cup of coffee together, to bump into each other, and then there's really more incentive for us to work together as a unit.
Dr. Scarcelli and Saeedi expect big results when they and so many more colleagues from the University of Maryland, Baltimore and the University of Maryland, College Park occupy the entire 4th floor of the new 4MLK Science Building and form the Edward and Jennifer St. John Center for Translational Engineering and Medicine. Center scientists will bridge the gap between research and development in the lab and the use of technologies in clinical settings. At the same time, expand experiential learning, create joint degree programs, and integrate multiple disciplines into a bench-to-bedside ecosystem.
My hope is that we'll find new applications for this type of technology, and which basically means that we'll need to build different instruments. The interbreeding between the clinical problems and what the technology can achieve is what I hope will spur from this.
It's really exciting to think about what this is going to look like, right? And like what kind of collaborations we're going to have, not just within, our space, we're both working on the eye, but, with with people looking at image processing, people looking at other aspects of engineering and other areas of medicine. And that sort of cross-pollination is what this is all about.